Welcome AC Circuit students. This video recording is a demo of calculations and also circuit measurements with a Picoscope appropriate to a resonance measurement lab assignment. So we're going to start with just a basic review of resonance calculations, and for that I'm showing my SMath sheet here. As we all know, resonance occurs in a circuit when we have both a capacitor and an inductor, and it occurs at a frequency for which the inductive and capacitive reactances are the same. So using that, one way to make it easier to calculate resonance for a particular selection of components is to just give yourself a selection of various values of components. I've labeled mine in terms of what components I happen to have. I happen to have a 100 millihenry inductor or 0.1 Henry, and I have a couple of 0.1 millihenries. So I have a 100 millihenry and a 0.1 millihenry. I have 2.1s. And so I've expressed these in scientific notation as just inductor 1, L sub 1, L2, L3, inductor 1, 2, and 3. I have a lot of capacitors and of varying values. And so I've just numbered them. And when I want to use one of them in my circuit, I just see which one there is. And then I can use the value of the variable down in my calculations to say, hey, if I chose, say, capacitor C1, which has a value of 4.7 nanofarads, what would my capacitive reactance be, and how would that influence my F resonance? So I define my total inductance and capacitance. If I wanted to put some inductors in series, I would just add them. If I wanted to add up my capacitors, I would of course have to place them in parallel. If I placed them in series, I'd get a lower value. So I could use my parallel or series combination formulas respectively for inductance and capacitance if I wanted to use multiple ones in my circuit. And then last but not least, I calculate the inductive and capacitive reactances using my formula for reactance, 2 pi times the given frequency times total inductance or total capacitance, and in the case of capacitive reactance I put this whole expression in the denominator of a fraction 1 over, so hence the -1. So just a glance at my inductive and capacitive reactances, this gives me an idea, since these are going to combine. I'm setting up for a series resonance circuit in my protoboard. I can get a little bit of an idea of what I'm going to get in terms of my total impedance. So in this case, my capacitive reactance is less than my inductive, so I would, if I were going to calculate a Z total, for instance, I would end up having a net inductive impedance in this particular circuit, given that these are in series. Okay, most relevant from the standpoint of my lab, I've taken these two expressions, my x sub L and x sub C, I've put them equal to one another, used a little algebra, and come up with a formula for resonance frequency. So this is just drawing on my defined values of whatever my total inductance and capacitance I choose to use. And so based on this selection of inductor and capacitor that I have here, I've got 100 millihenries, 0.1 Henry, and I've decided to use a 2.2 nanofarad capacitor in my circuit. I'm predicting that I'll have a resonance frequency of just under 11 kilohertz, 10.7 kilohertz. And so I can see for a given frequency whether I'm going to have a net inductive or capacitive reactance in my circuit, given that I'm going to put these in series. Okay. So the nice thing about an SMath sheet is if I choose a different component, all I have to do is change the subscript and I'll immediately know what how my resonance frequency is changed, and that's going to be of great help to me when I go and set up my Picoscope measurement parameters to do some measurements on this circuit. So I'm going to take a pause in the recording, and then I'm going to switch over to my Picoscope. I will have a built circuit with these values of components, and we'll start exploring some measurements that correspond to these calculations of resonant frequency, and also take a look at how the Q value of this circuit, so the reactance values of my non-dissipative components, my inductor and my capacitor, compare to the total resistance in my circuit, and what that looks like in terms of the bandwidth of my resonant circuit, or the frequency spread over which I'm dissipating how much power. So stay tuned for that. Again, a little pause, and I'll be coming back with my Picoscope display view. Okay, as promised, I am back showing my Picoscope display. At this point, I have my Picoscope turned on, but I have not enabled either one of the measurement channels, so we're not seeing anything. They're both turned off. And as I said earlier, when I was visualizing or displaying, my SMath sheet, I'm using a 2.2 nanofarad capacitor in series with 100 millihenry or 0.1 Henry inductor, and I am going to power those using a sinusoidal voltage signal from my arbitrary waveform generator here. And I'm going to look at how the voltage drop over the whole circuit, and then the voltage drop over a series resistor that I've placed in series with my, we'll call it my resonant tank, my inductor capacitor series couple, and how the voltage signal or the voltage drop over that resistor compares to the voltage drop over the whole circuit. Okay, so basically I have a capacitor and an inductor in series. Both are in series with, in my case, a 100 ohm resistor. Now, something important to remember with our AWG, and I'm pulling up my signal generator here now, my arbitrary waveform generator. The output impedance of the AWG on our Picoscope, our 2204 Picoscope, is about 600 ohms. So what that means is when we're looking at especially the Q factor of a resonant circuit, we need to remember that we've already got a 600 ohm resistor in series with whatever circuit we build. So, we've already got a good bit of what's in pure resistance in this circuit. So if we look at the how steep our resonance peak is, it's always going to be limited by that 100 ohm resistor. Now, one of the nice things is we're not going to get a dead short at resonance either. So that gives us a little bit more flexibility when we're scanning through our resonance circuit. We don't have to worry quite as much about having to include a current limiting resistor, which is why I'm able to use a resistor as low as 100 ohms for this series circuit. Because of course, as we know, as we go through our resonance frequency, if I've predicted things right, at about 10.7 kilohertz, the net impedance of my capacitor and inductor will go to zero or nearly zero, because we do have a little resistance in an inductor, and so the total impedance of my circuit should be purely resistive, and 100 ohms plus the 600 coming out of my AWG. So that's what we're going to explore here. So I'm going to select a sine wave, of course, and I'm going to start with 1 kilohertz. And so now I'm powering my circuit, but of course I can't see anything because I don't have anything turned on. So I'm going to start by turning on my channel that's measuring the whole circuit. We'll do auto, and of course I haven't enabled a trigger, so it's not showing anything. So now we're triggering on the midpoint of the rise of my sine wave, and I'm not showing very much, so I'm going to adjust my horizontal scale. So voila, a beautiful sine wave. Okay, what's important about what we're seeing here? This is the voltage drop over the whole circuit. So let's take a look. We can see there's a little bit of noise here. We can smooth that out a little bit by oversampling on our signal there, which we can get to with our display over on A. Okay, so now we can see a little bit better. So this is the whole circuit. We're asking the Picoscope to give us a 1 volt amplitude. Let's see what it really gave. No, pretty close. So we're seeing a little bit of sag in our Picoscope. So it's giving us, it's well centered. We don't have a DC offset to speak of. And we're getting about 975, 76 millivolts when we asked for 1 volt. So we have a reasonably high impedance circuit. So what's causing that impedance? Well, we got 600 millivolts output impedance out of our AWG just in the Picoscope itself. We have 100 ohms resistor in series, but the majority of our resistance is coming from the reactance of our capacitor and resistor. How much reactance? We can go back to our sheet, our calculation sheet, and put in 1000 hertz, and then take a look at the reactances, and we can see that at this point most of what is limiting current flow in our circuit and in fact controlling the sag in our Picoscope is our 2.2 nanofarad capacitor. It's providing about 72,000 ohms of reactance, a resistance to current flow by means of the fact that the current is charging and discharging the capacitor instead of flowing or dissipating. So it is a net capacitive reactance at this point. Okay, so what else might we want to know about our circuit? Well, we might want to understand what the voltage drop over our series resistor is. That's kind of important because we know that the voltage drop over a purely resistive component and the current flow through it should be in phase. So if we look at the voltage drop over our resistor, we're going to get an idea of what's the current doing. It's like a little current measurement device. So I'm going to go to auto and let the Picoscope figure this out for me, and rather than trying to scale it. And oh my goodness, if we look at the scale, full scale of our red signal, our channel B is only 50 millivolts and is not very big at that 50. We'll oversample a little bit to smooth it. So we can use our ruler bar and say we've got an amplitude of not even 1 millivolt. Very tiny. Well, that shouldn't surprise us given what we calculated for resonance. So if we come back and go back to our calculations, we've got the equivalent of something like 72,000 ohms of resistance in series with our little 100 ohm resistor, which is downstream in the circuit. And so we've dropped most of the voltage over the capacitor. It is totally expected that the resistance, or excuse me, the voltage drop over our 100 ohm resistor isn't going to be very much at that frequency. Okay, so let's put in a frequency that's a little closer to resonance. Let's go to, say, 5K. Okay, two things happened. First, we didn't see a big rescaling. We're still at 50 millivolts auto scale on our channel B, the voltage drop over the resistor. We'll adjust our horizontal scale a little bit, but we saw that the amplitude increased quite a bit. So we went from about 1 millivolt voltage drop to, oops, let's just use 1, to about 8. So we increased by 8 times. So what we did was we got closer to resonance and effectively decreased the total impedance coming through from our capacitor, and probably didn't increase the one from our inductor too terribly much. So let's do calculations. So we have now 3,000 ohms of reactance, inductive reactance, and 14 of capacitive. So much less than 72. So that's not surprising. So now we're getting more current through our reactive components flowing into our 100 ohm resistor, and that's what we're measuring the voltage drop over. And something else we're going to start seeing as we're able to visualize these two waveforms a little bit better is we're going to start seeing a shift in the peaks versus one another. So our channel B is representing the voltage drop over our resistor. It's also giving us insight into the phase of our current. And so as we go from a circuit that is net capacitive reactance to net inductive, we should start seeing the position of the peak of our channel B shift from basically to the left of our whole circuit voltage drop to the right. So our lagging leading relationship is going to change. So let's go ahead and see what happens as we inch on up a little bit closer to resonance. Let's get a little bit closer. Let's go to 10K. Okay, noteworthy, we've seen now a scale change. Now we've got 100 millivolts, which I'm kind of circling with my cursor here, on my channel B. And I can go ahead and measure with my rulers. So now I have an amplitude of the voltage drop over my resistor of 60 millivolts. So I went from 8 to 60. I'm within about 1 kilohertz of resonance. Still a lot less than the total circuit, 60 millivolts versus about 800. Now remember, we've still got 600 ohms of resistance effectively through the AWG, and we're not quite at resonance. Let's spread our scale out a little bit and see how much closer we can now keep an eye on our phase relationship a little bit. You can't go by the visual separation because of course we've changed our scale, but we're 21.77 microseconds difference. So we can get a phase angle using our calculator here. 21.77 times 10 to the minus 6, and we're using a frequency of 10,000 hertz, so I can just multiply by 10 to the third times 360. So 78 degrees apart. So we're going to see how those two change as we get even closer to resonance. So let's go ahead and move very close. And I'm going to take a pause as I move this around. Okay, here we are again. I am creeping up on resonance. So we were at 10.5, now I'm going to do 10.6. Oops, what you're seeing is actually 11, where I've a little bit overshot it. Okay, 10.6. Trying to move things around so they're not all in the way. Okay, at 10.6 we're still net capacitive, so we're still kind of on one side of resonance, and we're just gonna visually look at the relative peak positions as we kind of creep up on resonance. Again, we have a 100 millivolt scale for our channel B, so I'll go ahead and adjust that so you can see it. So we now have nearly 100 millivolts. We have 91.78 millivolts amplitude for our voltage drop over our resistor, and compared to only 552 approximately millivolt voltage drop over the whole circuit. So the fraction of the total circuit voltage drop that is being taken by our 100 ohm resistor is more. It is the resistor is contributing to a greater and greater fraction of the voltage drop as the net impedance over our reactive elements drops as we approach resonance, our series resonance. So we're going to creep up on this in effectively 100 hertz increments. So we're going to go from 10.6 to 10.7. And we've had another scale change. So now our channel B is scaled up to 200 millivolts. So now it went up about another millivolt, and the total voltage drop over the circuit is now 471. So we lost more of that capacitive reactance, and our peaks are drawing closer together. So let's creep up a little more. Aha! Another scale change. So now we've only got 500 millivolts full scale on our total circuit, and our pure resistor didn't have a voltage drop didn't have a scale change, but now basically a quarter of the total circuit voltage drop is being taken by the resistor. We have 100 millivolts being dropped over the resistor, 400 over the total circuit. Let's get even closer, or maybe overshoot it. Let's do, and I'm changing my frequency each time. Okay, 10.9, another small incremental change. We're going to go up to 11. Okay, so here we are pretty much at resonance. How can we tell? First of all, we can go back to our calculation sheet and say, well, it's a little bit more than what we calculated, but it's very close. We do know that we have at least 50 ohms of resistance in our inductor that's changing things on our Y scale, but we also know we have a fairly wide range for our inductor and capacitor. So those values of 2.2 nanofarads and 0.1 Henry may not be exact. So that will contribute to a difference in our exact resonant frequency. But generally speaking, we can tell we're at resonance because our total circuit voltage drop and the voltage drop over a pure resistor are almost completely overlapping. They're completely in phase. That's because the impedance or reactance of our inductor and capacitor have completely canceled out. So no imaginary component here. So it's purely resistive circuit. Why aren't they totally overlapping? Why is the total voltage drop of the circuit not exactly equal? That's because we have other resistive elements in the circuit. So at this point, at resonance, our 100 ohm resistor is contributing to about a third of the total voltage drop measured in the circuit. Why isn't it 100%? Well, we do have our output impedance of our AWG, and we do have at least a 50 ohm resistor, real resistance associated with our 0.1 Henry inductor. So that's 50% of what we have of our deliberately added 100 ohm resistance. But the output impedance of our AWG is contributing something that is not accountable necessarily in our calculations. Okay, let's go ahead to a higher frequency. So as we go to higher frequencies, the reactance of our capacitor is going to drop, and the reactance of our inductor is going to go up, and we should see our signal B start to shift over to the right. The peak will go to the right, and so we'll go to a different lagging leading relationship. So let's go to something that's clearly on the other side. Okay, so now we're give or take 1 kilohertz to the other side, to the higher frequency side of resonance, and you can see that our peak, I'll use the sliders, our peak for our channel B, our red curve, is now to the right rather than to the left of our total circuit voltage drop, and has now decreased again. Now we're at only 53 millivolts voltage drop over our resistor, and the total circuit voltage drop has gone up because our total impedance is going up again, which means the picoscope is not sagging as much. So using our oscilloscope, using a pure resistor in series with our resonant tank, our inductor capacitor resonance series couple, we've been able to demonstrate that our as measured resonance frequency is very close, is within component tolerance error, very likely of our calculated resonance. Our measured and calculated are within tolerance. And we've shown what would be the expected phase relationship changes as we go from a net capacitive to a net inductive total impedance in our circuit, using the voltage drop over our resistor as an indicator of our circuit current. So we're going to take another little pause, and then we're going to resume with an introduction or a demonstration of the frequency-based display available in your Picoscope. These are known as spectrum analyzers. So So far, all of our exercises with the oscilloscope have been a time-based. So I'm waving my cursor back and forth. We're looking at time on the x-axis. So we're looking at amplitude of some voltage signal as a function of time, and we're capturing the waveforms by sampling at a particular rate. That's how an oscilloscope shows us these beautiful static waveforms for something that's actually changing very quickly. In our case, that is changing at 12 kilohertz. So we can look at frequency on the x-axis as opposed to time. And resonance is a great time to do that because everything with a resonance couple or a resonance circuit is frequency dependent. We know that things change dramatically with very small changes in frequency as we get around resonance, more so the higher the Q factor of the circuit. And we just demonstrated this by creeping up on our resonance frequency by incrementally changing our applied frequency to the circuit and seeing how big the changes were in the relative voltage drops over our series resistor versus the total circuit. When we come back and take a look at the spectrum analyzer, we're going to look at frequency on the x-axis, and we're going to get an instant snapshot across multiple frequencies at the same time of how these voltage signals are responding. So we'll go from a time base to a frequency base, which is where you get these very exciting resonance plots, and how we can look at things like high and low pass filters. Looking farther into the future, there's a lot of circuits and devices that are specifically intended to manage frequencies, and almost all of them make heavy use of resonance circuits to select just the right frequency that you want to use or maybe get rid of. So this is a good way to start looking at the frequency basis of managing voltage signals. So back in a flash. Okay, we are back from our small pause, and we are ready to start looking at our frequency-based measurement. You can see my Picoscope screen is still in scope mode, and that's shown by our little highlighted square that shows two superimposed kind of sine waves over here. You'll notice I've stopped the display down here on the lower left. You can see we'll have a little red square meaning stop, and a green triangle meaning go. This is the capture of signal by the Picoscope and its display. So right now what I've said is quit capturing data. I don't want to look at anything right now. And that becomes important when we start displaying things on a frequency basis, because we're going to start averaging and adding up multiple signals to make a better display. So in some cases we'll need to erase what we have already collected, and that needs to be done in maybe the right sequence of stopped and running, so we don't overwrite things. Just for ease of view. So that's something to start being aware of that we may not have used so much in the past is, are we collecting data or are we not? So right now we're not. So to switch to frequency mode, all we have to do is go to our third button over here on the upper left, and it says spectrum mode, and it says switch to a frequency-based instrument. Well, yes, I'd like to do that. It's waiting for data. It's probably not going to get it because I don't have any channels turned on. An important feature for our frequency-based data collection is what's called spectrum options, and we're going to go through that. So it's called FFT options, and the FFT means fast Fourier transform. And that's a mathematical way of processing things in the frequency domain for easier viewing and mathematical manipulation. And there's a lot of things in here that we'll use and some that we won't. Something important is what's known as spectrum bins, and it's basically the number of incremental frequency units that we're going to average on. And you can think of it as the higher this number, the more data points. These are binary numbers. And it basically is a measure of how many units of information are going to correspond to each frequency unit that the instrument looks at. That will define our spectral resolution. And for these experiments, we're going to stay somewhere between the 8192 and 512. And let's go somewhere in the middle. There's a window function that basically says, you know, for each frequency increment that we're going to gather data over, how do we want to treat the edges of that window? If you look on information in the Picoscope manual under frequency spectrum measurement, you'll see that the Blackman-Harris is noted as being good for general measurements, so I'm going to use that. And I can look in a magnitude, average, or peak hold mode. So I can basically, for magnitude, I'm going to collect the amplitude or magnitude of the voltage signals I'm looking at as a function of whatever frequency I'm looking at, or over a sweep of frequencies right at that moment. If I hit average, I will look at an average over a given span of frequencies, so it'll give me a smoother signal. But what we are really going to make use of to make our resonance plots is the peak hold, which is going to collect the highest value of voltage over a given time averaging interval or frequency averaging interval over our window, and it's going to hold it there. So this is like a peak hold, or a capture the high number over a range of measurements. We can display on the y-scale in logarithmic or linear. For the circuits that we're using, I've found linear is going to give me an easier to see display. If we saw a change in voltage signal over many orders of magnitude, obviously logarithmic would be better, and we would have the option to do a logarithmic in various decibel units, which we won't have this time. Okay, so we're set up looking to go to peak hold. We're going to use a Blackman-Harris general window on the recommendation of Picotech. So the next thing we need to do is look at, well, what frequencies are we going to look at? Well, right now our AWG it's only going to give us a single frequency. Well, let's see how things look at that single frequency. So we're going to turn the signal on, and let's go ahead and turn on channel A to auto, and we don't see much. Probably because we're looking at a 10 megahertz of full scale. So let's go to a 20 megahertz. Okay, wow. We imposed a 12 kilohertz signal, and we're looking at the output of the circuit, and we're noticing, wow, we're only getting a response for the frequency over which we're imposing a signal. Hey, that's pretty expected. I put in a signal with a 12 kilohertz frequency, and voila, that's what I'm measuring. There is no 10 kilohertz signal because I didn't put one in. I only put in a single frequency, so I only get a single peak. So that's pretty reassuring. So that's kind of a little intro to frequency response. Now, if I want to get rid of this peak hold signature, I come back over to my FFT options and hit magnitude, and then go back to peak hold, and it shouldn't come back. And I can stop the signal display or the data gathering now, and I'll put my cursor slider over. Okay, the important thing we're going to need to do next, if we're looking at gathering a frequency sweep to show our resonance peak, is to sweep the frequency. Good thing our arbitrary waveform generator will let us do that. So now we're going to look at something we probably haven't seen in the past, and that's sweep mode. So we're going to click active. Yes, we'd like to sweep. And I'm going to say I want to sweep up and down. So I want to start at some frequency below resonance. I want to sweep through the resonance frequency to something that's about the same number of hertz or kilohertz to the other side of resonance, and then come back. And then just keep going back and forth. And I'm going to let my peak hold feature continue to gather the highest value each time I go through. So, well, let's see. Where was resonance? I'll go back to my calculation sheet. Okay, it was at about 11 kilohertz. So I want to start maybe let's say 6 kilohertz below. So 6 below. So I'll start at 5 kilohertz total. And if I want to go to 6 kilohertz above, so 11 kilohertz plus 6 kilohertz is what, 17 kilohertz. Okay, so if I want to display all of that, I have to pre-select a frequency scale on the x-axis. So this isn't seconds, this is hertz, that's going to allow me to see my entire sweep. And it turns out these are preset. So I have 2, 3, 6, 12, 24. I'm already on 24. So 24 will capture my 5 to 17 just fine. Okay, and I'm going to go ahead and turn on channel B. So now I'm going to be collecting 2 signals, and they're going to auto scale. So we're going to get a little bit of funkiness as we collect signals because we're going to get a continuous auto scaling as we gather data, and we know we're going to get a tremendous change in the voltage signals as we approach resonance. We're also going to see an interesting artifact of the data collection where, depending on how our frequency scale that we've selected and our frequency resolution in our spectrum bins, how that interacts, we may get what looks like a whole bunch of little Gaussian curves as we collect data, but by using our peak hold, those will all end up averaging out using just their top value, and we'll end up getting a smooth curve as we sweep back and forth and continue to gather data. So let's see, are we ready to start? We've got our spectrum bins collected. We're doing our general Blackman-Harris window. We're on peak hold. We're going to display with a linear scale. We've got an X scale that should capture our whole sweep. We're going to sweep from 5 kilohertz to 17. We're going to sweep up and down. We've got both of our signals turned on. We're on auto. Okay, so we should be ready to gather. So let's go ahead and start sweeping. Auto. Oops. What haven't we done? We're sweeping. Voltage is changing frequency in our signal, but we're not seeing anything. Oh my gosh. Well, the circuit's changing, but we're not collecting any data. See, we're still on stopped. So let's turn our signal off. Let's start collecting data. So now we can see the red and the blue data traces are there. They're just collecting whatever's going on at 5 kilohertz. In fact, at nothing, because we don't have a signal on. But now we're ready to collect. So if I turn my signal on, I should start seeing something. And there we go. We're getting all kinds of notes of channel overage. And we're collecting data very, very quickly over this range. But as we can see, as what's happening is we're sweeping the frequency back and forth and collecting voltage signals. We keep hitting a channel over voltage because we keep having to switch scales too quickly. But as you can see in our blue channel, which represents the total circuit voltage, we're now beginning to get a signal with a dip in the middle. And even though we're auto scaling, we're kind of staying on what seems to be more or less a perpetual 2 volt consensus Y scale. The voltage drop over our resistor, it keeps jumping up and down because every time we sweep past, as we go through this resonance point, which is looking a lot clearer now, it's auto scaling from a 50 millivolt scale to a 200. So that's the the reason for the jump. But notice how we went from something that was a bunch of data collection Gaussian humps that didn't mean anything to something that's looking a lot more like a resonance frequency sweep, voltage versus frequency. So as we let our Picoscope continue to collect more and more signal, we can take note of kind of what we're seeing. And this is sweeping very quickly, so I'll have to go ahead and stop it. somewhere where it's scaled up and we can see it clearly. So we've stopped collecting and we've stopped sweeping. So we can see this clearly enough at this point. I wouldn't want to try to gather bandwidth data because it's still pretty choppy here. And we can do things like adjust our spectral resolution to do that, to get a smoother curve as we go on. But first thing that's important is we can see we have a characteristic resonance frequency response. So the first thing we can do is we can check and look on our blue curve and our red curve and say, all right, where are we seeing the low point in the dip in the case of the total circuit voltage? Because at resonance, we have the lowest total impedance in our circuit, so the picoscope's going to sag the most, so we should see a voltage low for our total circuit voltage right about resonance. So we're using our slider, which is now telling us frequency, and let's look at the low point. And what is that? 11.02, almost exactly what we measured with a scope. But this was a lot easier. We just used a frequency sweep, we let it collect some, and boom, there's our resonance peak. Something else that we can do is we can use the full circuit to measure bandwidth. We've got a more or less a good enough signal to do that. So for that, we would measure the amplitude of that peak using the baseline. So what was our voltage well away from resonance? What was it at resonance? What's that difference? So we have about 288.7 millivolts. So there's our full scale. And we know that we define bandwidth as the half power frequency. So if it's half the power, our voltage is going to ratio by 0.707, kind of that RMS relationship. So if I do 0.707 times 288.7, I get 204. So I would, if I wanted to position that on my blue curve, I would do 204 minus 288.7 plus. So I would come down 84 from my non-resonance point, and then I could pick the frequencies at which I intersect that. I've got half the power. So basically here's my low power. This is my 3 dB frequency here. So this would be full frequency, no decibels lost. This would be the point on my curve, the frequency which I've lost 3 dB or half power. So if I look at the difference between this frequency, my F1 or F critical 1 and 2 is another word for it, I've got about a 1.78 kilohertz between those two frequencies, those two half power frequencies. So that defines the bandwidth. So basically, if I were trying to say select frequencies or exclude frequencies, this circuit would say basically anything that is within this 1.78 kilohertz range of resonance is going to be at half power. Or if I'm selecting them through the circuit a different way, they would be at full power and everything else would be at half or less. So that's another way to take a look at that. We don't want to make any measurements on our resistor circuit, but we can take a look and notice that it is following the totally expected kind of shape. We're definitely seeing a high point in our voltage drop over that resistor when we have the low point over our whole circuit. So that's the expected resonance relationship. And in fact, we could even go ahead and see how these values correspond to what we measured on our scope. So we're seeing a voltage drop of about 50 millivolts at resonance and versus our whole circuit of 104. So about, again, 30%, give or take a little bit over 30% of our total circuit voltage drop is the resistor as opposed to the two reactive elements at our resonance point. So that is about it for our brief tour of using our frequency-based data collection, or our spectrum analyzer on our Picoscope. If we want to get better and better signals, things that we can do is, for instance, first we'll go ahead and get rid of those. Kind of go running and stop to clear our screen. We can do things like change our data collection interval. We can change our frequency interval that we use for sweeping slower and faster. And we can sweep for longer times and improve our signal a little bit. So we can leave. I'll go ahead and run another one, take a pause, and then show how changing our collection parameters can give us a little bit smoother signal. Okay, we're back from a little pause, and as kind of a next item in showing how to collect frequency sweep plots with our spectrum analyzer, or frequency-based data analysis on the Picoscope, we're going to look at what happens when we collect on a much shorter, much smaller frequency increment. So before we had a 10 hertz increment of frequency over which we were sweeping. This time we're using a frequency increment of 100 millihertz, or 0.1 hertz. So every 0.1 hertz, the AWG is going to move frequency, and then we can collect data. Then it moves another 100 millihertz, then we can collect data. So what that's going to do is give us the potential for a much higher resolution signal. To go along with that, I've actually reduced the spectrum bins, which is going to have the effect of having us just see the top of whatever the range of voltage outputs were for that frequency range. And of course, we're in peak hold. We're going to look at linear rather than logarithmic output. We've got our same 5 kilohertz to 17 kilohertz. And we are, of course, running and collecting data now. So if I turn my signal on, you should start seeing a little bit different looking plot. I've also fixed our scales at 1 volt for the whole circuit, and then at 100 millivolts for just our resistor. And so you can see we're collecting, rather than having those kind of Gaussian plots that said, hey, here's the range of voltage amplitudes over this frequency window. We're only seeing the very top, because we're looking at snapshots of 0.1 hertz, and the Picoscope is collecting just the high point in that 0.1 hertz range. So it's kind of like we're drawing a line. And so all we've done is changed the speed with which we sweep, the number of times we basically, as we sweep, what we're doing is we're moving and stopping and moving and stopping. So we're moving less and stopping more, and then we're collecting less, and we're only displaying the high number. So this has the effect of just drawing a line the first time we go through. So effectively, we're gathering a lot more data with each sweep, because we're stopping and gathering more often rather than just sweeping. So we don't have to sweep back and forth as many times. So it's basically all a matter of how much data you want to collect. We're going much slower as well. You can see we're moving much slower over our sweep range than we were before. We could get to a nice curve either way. If we sweep faster, collect fewer times per movement increment, we just have to sweep more times. So eventually, one way or another, you have to collect the data you need to get a good resolution to make your measurement. A little measurement theory there. And if any of you have taken chemistry and are thinking this sounds an awful lot like collecting multiple spectra with some, optical spectroscopy like infrared, it's following the same principle that fast Fourier transform is used to do optical spectroscopy, as well as just frequency sweep spectroscopy. Basically, in both cases, we're looking at the frequency of something. In our case, it's the frequency of a sinusoidal electrical signal. In optics, it's going to be the frequency of light, both measured in hertz. So you can see we've swept up and now we're sweeping back down, and you can see the blue curve here. We're smoothing it out as we're collecting just the high point. A lot of those little valleys are coming out. But we already have something that is good enough to make a measurement with. For instance, we could get our total peak or our total reduction in total circuit voltage is about 466 millivolts. So already we could define a half power by multiplying this by 0.707 and start to get a bandwidth. Probably go a little bit further there. You can see that we're a little bit asymmetric on one and the other side of resonance. It's much easier to measure a bandwidth than to look at the appearance of our resistor voltage drop. We'll use the sliders there, the ruler. So we can see again we've got 74.18 millivolts on our resistor voltage drop, as opposed to 225. So again, we're once again seeing about 30% of the total circuit voltage drop at resonance is being accounted for by the voltage drop over our 100 millivolt resistor, plus whatever output resistance, of course, is in our AWG. But we could at this point stop our data collection and stop our sweeping. And we could go ahead and we could use two different methods now of measuring bandwidth. We could again do it like we did earlier in our recording on the full circuit. And for this, I would use basically something in between, kind of take an average of the voltage, total voltage drop over the circuit well away from resonance, both on the high and low frequency side, and then of course, my lowest voltage drop. So 457.7, we'll call it. Get my calculator out. Still have to do a few calculations. We'll call it 458 millivolts total difference from no resonance to resonance. In this case, what we're looking at is basically the drop in impedance as we go through. So we could look at the blue curve as the impedance of the total circuit. We're getting a reduction in that. We're getting an increase in current, which is why the voltage drop over a resistor is increasing. We can apply our 0.707 to that total peak value, 323. And so we can subtract it from our upper baseline, 458 plus. So we'll come down 138. Right about there. And we can define our half power frequencies. So right here, we've looked at from here to here is effectively a 3 dB loss reduction. And so here's our half power frequency on the low frequency side and our half power frequency on the high frequency side. And so the frequency difference between those is being reported up here, and that's our bandwidth. So we're measuring pretty much what we did before, 175. And we should be able to do the same thing if we took our red curve, if we wanted to use the voltage drop over the resistor, except in that case we'd be going the other way, looking at what point do we have half the value from the base to the peak. Now in this case we never did get or at least the scale is making it harder to see where we actually went mostly flat. So it's a little bit harder to call, how high is this, but we could get something, approximate. So we have something in the range of And again, I'm gonna average on both sides. Most of the ideal curves show these equal. I probably should have extended my frequency sweep out a bit more. Let me go down a little bit. So I am showing a height difference with the rulers of 600 or 68 millivolts. So that's my biggest voltage drop. So 68.707 times 48. If I added 48 to my baseline here of 6 point, we'll call it 34 plus, I'd go to 54 on my upper, 54.4 is what I calculated, give or take. So somewhere right in there, which is right about the same position I calculated using my total circuit current. And this is giving me a little bit narrower bandwidth. It's a little bit, you know, we have a little bit of error of where the baseline was, but it's fairly close. We have about a little under or a bit over 1.5 to 1 3/4 kilohertz, depending on how we make the measurements. They're pretty similar. And in both cases, what we're looking at are the frequencies that span the point at which we would have half the power being dissipated, either whole circuit or over the resistor. So that gives us an idea of the frequency span over which we're getting this big change in impedance in different parts of the circuit. And this lets us select where we're going to send signals in our subsequent circuits depending on their frequency. And of course, for those of you who might go on to RF studies, that's fundamental in transmitter and receiver technology, as well as any kind of signal processing. So this concludes our quick demo on use of our Picoscope and calculators to evaluate resonance in a series resonant circuit. So just as a quick recap, what did we do? We started with our calculation sheet. We gave ourselves a selection of components. We calculated total inductance and capacitance. Of course, had we wanted some intermediate value, remember you can always add things in series and parallel to get values that you may not have in your component box. We got an idea of whether we were going to have net inductive or capacitive reactances. And of course, given that we have a series circuit, of course, those are just additive. And most importantly, we pre-calculated resonance. We did a little bit of work with our scope, comparing waveforms for voltage drop total circuit, voltage drop just over our series resistor, which is predicting what's going on with circuit current. Then we went to our spectrum analyzer. We swept the frequencies over a range that started well below and went to well above resonance. And so we were able to look at the frequency response of our circuit, different parts of our circuit, namely the whole thing versus just the resistor, and get an idea of how sharp our resonance peak or trough was. And of course, that bandwidth is related to what's known as the Q factor. So effectively, if we wanted to broaden our trough, we might increase the number of series resistors we put. And we can predict that by looking at the magnitude back on our calculation sheet, of course, of our reactances versus the total resistance. So if we want a nice sharp peak, we want to get rid of the resistance wherever possible and have big reactances, and then vice versa. So if I wanted to sharpen this peak, I would have used a smaller resistor as my current indicator resistor, maybe a 50 ohm. Of course, I would have been limited by the output impedance of my AWG ultimately, but I could have used a bigger inductor or a smaller capacitor if I had had one, or used a series parallel combo to achieve that. So that is it for resonance calculations, Picoscope measurements, and we will continue to use the spectrum analyzer to take a look at the frequency response of other circuits, namely passive filters, high pass, low pass, and get an idea of which one we're looking at depending on what we're measuring. So stay tuned for that in future videos and modules for your course.